Some very exciting things we are learning here in Chapter 7. Let's go to practice number 4. It says the average number of minutes spent on a particular tablet app is 8.2 minutes. The standard deviation is 1 minute. A sample of 60 app use times are randomly selected. Okay, so we're talking about a tablet app. Of course, we all know, they track all of this data, whoever creates these apps. And so let's say this particular company or person who made this particular app is able to gauge how long people use the app whenever they do. And so it turns out the average number of minutes that people spend on it is 8.2. The standard deviation is 1 minute, and they're going to take a sample of 60 app use times. So let's record those things. We've got mu is 8.2, sigma is 1, and our sample size is 60, n equals 60. What are we going to do here in practice number 4? Okay, part A, we're going to find the 80th percentile for the sample mean time, round to 1 decimal place. Okay, well, this is going to work just like the previous chapter. We're going to work backwards for a percentile question. So we're going to begin by saying the probability that big Z is less than little z equals 0.80, our 80th percentile. And we're going to go for our table. We're going to find the closest thing that we can to 0.8 and work backwards. And if you do that, you'll end up with Z equals 0.84. And, well, let's just maybe do that together. No harm there. If we find the closest thing we can to 0.8, we'll kind of come into this range and say, okay, there's 0.7967. Okay, this one right there, 0.7995. That's as close as we can get to 0.8. And guess what? That's 0.84. So there we go. The idea is we're trying to solve for x bar. So we're going to use our formula, our new formula for the z-score with the central limit theorem. We'll say, all right, so the z is 0.84. We're looking for x bar minus our mu 8.2 divided by, and there we've got sigma 1 divided by the square root of n, which is 60. And we're going to have to solve this equation for x bar. Now this can get a little bit tricky for people when you have this fraction down here, but I'm going to recommend treat it just like this was one number, just like we did in the previous chapter. So take that whole thing and multiply it over this direction. And you don't have to figure out what 1 over the square root of 60 is yet. I would actually recommend you don't round this in the middle of the problem. Just go ahead and take it exactly as it looks, multiply it over here to the left side. So that would look like 0.84 times 1 over the square root of 60. And that equals x bar minus 8.2. Again, I really don't recommend you round anything right now. Just leave it like that. At that point, we can add the 8.2, 0.84 times 1 over square root of 60 plus 8.2. And now grab your calculator and compute that guy right there. I'll do the same. 0.84 times 1 over the square root of 60 plus 8.2. Let your calculator do the rounding here at the end. I got 8.308. It said to round to 1 decimal place. So 8.3, or if you're wondering what the units are, that would be 8.3 minutes. The 80th percentile. Okay, very nice. What does part B have for us? Find the probability that the sample mean is between 8.0 and 8.5. Okay, we have not done a between kind of probability yet in this chapter, so it's probably a good idea. It's good to practice all the different styles. We do less thans, we do greater thans, we do betweens. So let's try this out. What we're saying is X bar is going to fall between 8 and 8.5. And so how do we proceed? What we need to do to get started is find the z-scores for both 8 and 8.5. So let's start off with 8. Think of X bar as just equaling 8. Take it as equal to that smaller one. We're going to do the same thing for 8.5 in a moment. Let's find the z-score that goes with the 8. So we'll plug that into our formula. Z equals 8 minus 8.2 over 1 over the square root of 60. Grab your calculator and use parentheses like so, and you will get negative 1.55. If we find the z-score that goes with the 8.5, let's just go ahead and do that right now. So taking X bar as being 8.5, z equals 8.5 minus 8.2 over 1 over the square root of 60, parentheses of course, and you will find that z-score is 2.32. And now we'll find the probability between these two z-scores. And I'll just go ahead and show you how we would begin that. So we'd say, okay, the probability that big Z is between negative 1.55 and 2.32. So 1.55 less than Z less than 2.32, our smaller Z score and our bigger Z score. And how are we going to go about that? Well, we take the probability that Z is less than 2.32 and subtract the probability that Z is less than negative 1.55, the bigger Z score minus the smaller Z score. And at this point, we'll reach for our table and figure out the probabilities that go with 2.32 and negative 1.55. I'll just go ahead and show you guys, but I encourage you to look these up as we're working through this together. So for 2.32, I get 0.9898, and for negative 1.55, 0.0606. We happen to have these like repeated digits in both. A coincidence. Kind of funny. So when you subtract, the probability between those two z-scores is 0.9292. So the chances that the sample mean is between 8.0 and 8.5, there you go. Almost 93%. There you have it. Okay, we've got one practice problem left. Number 5. Number 5, I'll tell you right here at the beginning, this is the crown jewel practice problem example in this chapter. And honestly, this is the crown jewel of all the normal distribution problems we've done so far. This problem is amazing, and it will really show us how the normal distribution and the central limit theorem gets applied in real life situations day to day. It's happening now around the world. Okay, I'll go ahead and read it. A factory produces chocolate bars claiming to be 1.55 ounces. Okay, so we got this big factory. They're making chocolate. In case you didn't know, Hershey bars are 1.55 ounces. Okay, so it says the manager of the factory knows that the actual weights are normally distributed. The mean is 1.55 ounces, but with a standard deviation of 0.02 ounces. Okay, so they know when they make these chocolate bars that sometimes it's not exactly 1.55 ounces. Okay, that's probably not a huge shocker. Sometimes there's a little bit more chocolate in that bar than there should have been. and sometimes there's a little bit less. The mean is 1.55, but they've got this very small standard deviation, indicating that it really doesn't stray very far from that, at least not very often. Okay, so where is this going? Each morning, a carton of 20 bars is weighed. So they take 20 bars and they weigh the whole thing. The manager has ordered that production be stopped for the day if the contents weigh less than 30.8 ounces or more than 31.2 ounces. What's up with that? Okay, so um, the manager would stop production if the machinery that is creating these chocolate bars has like gotten out of tune, like it's gotten out of whack a little bit. So in that case, they would want to come in and recalibrate the machinery. So, over time, maybe, the chocolate bars that are created weigh too little, or maybe they weigh too much. They're putting too much chocolate or too little chocolate. But you can't base that on just any one particular chocolate bar because, something, kind of bizarre might happen with any one bar. So instead, they weigh a carton of 20 bars. And if that carton weighs less than 30.8, then they know something's up. Or if that carton weighs more than 31.2, then they know, okay, something is going on with our machinery. We need to shut everything down. We need to recalibrate our machines. And then we maybe can start production again the next day, let's say. So the question there at the bottom is, if the factory operates for 200 days of the year, on how many days does the manager stop production? Or maybe we should say, on how many days do we expect the manager to stop production based on the probability we'll calculate? Okay, how are we going to begin? Well, a couple things we know right away. We know that the mean is 1.55. We know the standard deviation, sigma, is 0.02. And we know that the sample size is going to be 20, right? Because they weigh a carton of 20 bars. So there's your sample right there, sample of 20. Now, what we're going to have to figure out and be careful with is, okay, then what are the sample averages? So those are going to be based on the total weight of those 20 bars. So how are we going to do that? Okay, so take a look again at those numbers. So if it weighs less than 30.8 or more than 31.2. So if it weighs, let's say, exactly 30.8, but that's all 20 bars. So what is the average weight of a bar if the sample in total comes out to be 30.8 ounces? We're going to call that X1 bar, or X bar sub 1. So the total weight is 30.8. We're going to divide that by how many bars are in that sample to get the sample average. So here it's like we're kind of going back and literally taking an average. The total weight divided by how many bars there are. And it turns out if you do that, you'll get 1.54. So that would be the average weight of a bar at that minimum number of 30.8 ounces. We can do the same thing for the maximum weight of the 20 bars, 31.2. So we'll call it X bar sub 2, and we'll take, all right, 31.2, the total weight of the carton divided by 20 bars. So the average bar in that sample would be 1.56 when you divide those numbers. And you see my note here on the side. What do these represent? The average weight of a bar from those samples. We've got the lower limit and the upper limit. Okay. So really what they're saying is, when they say this 30.8 and the 31.2, they're saying from a sample of 20, let's be sure the sample average is not less than 1.54. And if we take a sample of 20, let's be sure the sample average is not more than 1.56. They just happen to give us these numbers because that's what they would actually do in the factory, right? That's easy for the workers. Just weigh the 20 bars. If it's less than this number, bigger than that number. Okay, but we need to know the average weight of the bar. What are we going to do with that? Well, maybe it's not surprising. We're going to calculate z-scores with those two x's. So let's start with x bar number 1, 1.54. Notice those are symmetrical about the 1.55. They're both off by 0.01, which is also maybe kind of thinking that's not surprising. So it's like they're allowing their average to be 0.01 away from the ideal kind of thing. Okay, anyway, let's go on. For x bar 1 of 1.54, let's calculate the z-score. So that z equals 1.54 minus 1.55 over 0.02 divided by the square root of 20. When you grab your calculator, use some parentheses, of course. And when you round it to 2 decimal places, you'll get negative 2.24. Okay, before we go to find the z-score for x bar 2, I want to stop here. And I want to find the probability that goes with this. So, do we want a probability less than this z-score, or do we want a probability greater than this z-score? If this would be more interesting if we were all in class together. So I'll just tell you. We want to find the probability less than, I'll cover this up just to not distract. We want the probability less than negative 2.24. Why is that? Well, go back and we'll read the problem. They're going to stop production for the day if the contents weigh less than 30.8. So if the average is less than 1.54, less than, so we say the z-score less than negative 2.24. And when you look that up on your z-table, negative 2.24, you'll get this number right here, 0.0125. So that's the chances that your average chocolate bar is less than 1.54 ounces in a sample of 20. Okay. Less than the lower limit. Okay, yeah. The lower limit is this, so we cannot allow it to be less than that. All right. Let's continue this problem. For x bar number 2, so this is as much as the most that we can get for our sample average is 1.56. And we'll go about it in a similar way. 1.56 minus 1.55 over 0.02 over square root of 20, parentheses like so. And you notice when you do this calculation, the numerator right there, very similar to this numerator. Here you would get, if you subtracted those, you'd get negative 0.01. While in this case, you would get positive 0.01. The denominator is the same, so what does that mean for the z-score? Well, you do that computation and you'll get positive 2.24, which is really not surprising, seeing as our x bar 1 and x bar 2 are symmetrical about the mean. So our z-scores are symmetrical about the mean as well. Negative 2.24 and positive 2.24. In any case, moving on, what are we going to do? Which type of probability do we want? Do we want a less than, a greater than? Go back and read the problem, and it says we stop production if the contents weigh more than 31.2. So we've got the greater than for this z-score, positive 2.24, which means to actually figure out that probability, we need to perform a complement, 1 minus z less than 2.24. Let's go ahead and look that one up. Positive 2.24 is 0.9875. And if we do 1 minus 0.0125. And you see my note there, okay, greater than the upper limit. All right, yeah. Now here you might notice, oh wow, it's actually the same probability, 0.0125. Yeah, and that makes sense because, we're thinking, well, we don't want it too high or too low, and it's going to be symmetrical about the mean. So the chances of being greater than this z-score are the same as the chances of being less than this z-score. Now at this point, we still haven't quite answered the question. We've done a lot of work, but we got to put it all together. So we found that the chances of being less than that lower limit and the chances of being greater than the upper limit are both 0.0125. So what's the total probability that we fall outside of the acceptable range of weights to our chocolate bars? Well, we need to add those together. So the chances of being less than the lower limit plus the chances of being greater than the upper limit, put it all together, and in this case you would get 0.025. So the chances of being outside of our acceptable range is this 0.025 or 2.5%. But still, that's not the question. The question is if the factory operates for 200 days of the year, on how many days would they stop production? Okay, so we think, all right, these are the chances for any one day. So what's the chances, or how many days might we expect if there are out of 200? So we'll take 200 total days and multiply it by that probability. What is 200 times 0.025? And you'll get, it's exactly 5 days. We didn't have to round that. If it was another problem, you might have to round this to the nearest day. I don't know. In this case, it turns out to be exactly 5. So on 5 days of the year, they expect that their machinery is off, either too low or too high, and they're going to have to shut everything down and bring somebody in and recalibrate and then open again the next day. Kind of moral of the story, what did we find? Kind of going back to the probabilities. So, if we were to graph a bell curve, and we can make it a little bit steeper to account for the fact that we're doing samples of 20. So, right, we expect that the sample average is going to be 1.55. So we'd put that right there at the center. What's happening is 1.54 and 1.56, well, that's symmetrical about 1.55. We think, okay, if our sample of 20, if the average is anything in between, then we are good. We want anything in between here is acceptable. If our sample of 20 gives us an average out here, then we know something's off with our machinery. Or if our sample is, the average from our sample of 20 is up here, again, something off with our machinery. So what are these probabilities? And we found this one to be 0.0125. And likewise, we found this one to be 0.0125. And so what's the total probability of something bad happening? Well, add them together, and then we account for the fact that there's 200 days that they operate. Okay. There you go, the crown jewel. This is happening day in and day out in factories all over the world. And what's cool is the people who actually work in the factory and the manager of the factory, they don't have to know anything about statistics, right? They bring in a statistician, and the statistician does the calculations, takes their numbers, right? Um, Says, okay, well, how far off of the average, do you think you want to allow things to be? Like, what's acceptable, what's not? So they make that decision. They tell the statistician, and the statistician says, okay, so at the end of the day, every morning or every night or whatever, you just need to weigh a sample of 20 of these chocolate bars. And if it's more than this number, something's bad. If it's less than this number, something's bad. And they don't need to ever talk to the statistician again. They just know what numbers they're looking for, and obviously they'll be in charge of recalibrating their machines and stuff. Okay, that's it. That is chapter 7.